Hey, welcome to the 32nd session of the Flipped Classroom for AP Calc. Today we're going to finish up Section 4.4, Part 2, Riemann Sums and Definite Integrals. We start off by talking about the average value of a continuous function. Basically, if f is continuous on a closed interval AB, and we divide that interval up into equal subintervals, in fact, an n number of subintervals of equal length, the length of each subinterval can be expressed as delta x being equal to b minus a over n. To find the average value, we can add up some arbitrary function values evaluated at some point ck in each subinterval. If you remember, this is what we did when we talked about Riemann sums. Next, you just take that sum and divide it by n, the number of subintervals, the same way you'd find any average. Mathematically, what you end up with is f of c1 plus f of c2 plus f of c3 all the way to f of cn divided by n. Okay, this can be written in a summation form as 1 over n times the sum of f of ck. There should be an I equals 1 and a k equals 1 if you want to use k, and an n on the top of the summation sign. Sometimes that's hard to do with our existing technology. Now, if we say that the length of each subinterval, delta x, that would be equal to the whole subinterval, b minus a, divided by the number of subintervals, n. Solving this for n, we get n equals b minus a over delta x. So take what we have mathematically, 1 over n times the summation, there's our k equals 1, and n of f of c sub k. Substitute n in what we had for n, and what we get is delta x over b minus a times the summation of f of ck. Now, since delta x is the same length of each subinterval, that means it's a constant. I can bring that to the inside of the summation sign, which yields 1 over b minus a times the summation of f of ck times delta x. Does anybody recognize what this summation of in blue represents? Okay. Well, in fact, that's a Riemann sum, which we studied in the first part of this section. So, and if we let the number of subintervals, n, go to a very large number, like infinity, then that Riemann sum would be the exact definition of the definite integral f of x dx. Dividing the definite integral by the b minus a, which is on the outside, we have that the average value of f of x on a closed interval ab is 1 over b minus a times the integral of f of x. That's it. Here's a sample problem. Let's find the average value of some function y equals the square root of 4 minus x squared on the interval negative 2, 2. Okay, so the first thing we would have to do would we have to find the definite integral, the area under this curve. Right now, we only have really two ways to do this. One is what we learned in the first part of this section, is we could take the sum of many rectangles and add their areas up, and that would be an approximation of the area under this curve. Well, we can do that on this, or another way we can do is we can recognize that this curve is really a geometric shape. What do I mean by that? Well, if I square both sides of this equation, okay, my original equation, y equals square root of 4 minus x squared, I get y squared equals 4 minus x squared. One might recognize that as the equation for the area of a circle, not the area of a circle, but of a circle. So if I'm just taking the square root of this, what I have is a semicircle. And it's very easy using a geometric formula to find the area of a semicircle. It would be a semicircle of radius 2, square root of 4, and the area of the circle, pi r squared, would be 4 pi. Half of that for the semicircle would be 2 pi. Now, just divide that 2 pi by b minus a, which is 4, and the average value of the function becomes 2 pi over 4, or pi over 2. Isn't that cool? Here's another one. Let's suppose I've got y equals 1 minus x on the closed interval 0, 1. Now obviously we can recognize that as a straight line. I've drawn it here with the red line. The shaded blue is the area under the curve, and we're going from 0 to 1. The area under the curve, I recognize this area as a triangle. Area of a triangle, 1/2 base times height. So that would be 1/2 1 times 1, which is 1/2. Divide this by the length of the interval, which is 1 minus 0, or b minus a, and I get the average value is 1/2. Okay, some properties of definite integrals. On table 4.5, page 370 in your text, there's a complete list of properties. Some useful properties are included on the next slide. All right, I Googled properties of integrals, and I got this. I will tell you there is a mistake in one of these, and I will point it out when we get to it. The first property says that if we take the integral of a function at a and a, the value of that integral is 0. Well, this makes sense because really what I'm doing is just taking the integral at a point, okay? And that would have to be 0 because the width of our interval would be 0. The next one says, and this we use a lot, notice the lower and upper bounds of integration here are switched. So how do I switch them back to b minus a? It's real easy. Just put a negative sign out in front of the integral, and these two things will be equivalent. Because basically all I'm doing then is if b minus a, if the width of my interval is 5, and I need to be -5, I can switch it by just putting a negative sign in front of it, okay? The third one on here says that the integral from a to b of a constant is just that constant times the overall length of the interval. Well, think about the constant. Wouldn't that be a horizontal line? Okay, and a horizontal line gives me a rectangle when I have interval AB, and the area of a rectangle is just the height, which would be c, times the base, which would be b minus a. Next property says that the integral of the sum of two functions is equal to the sum of the individual integrals of those two functions, as long as a and b are the same in both cases. And there's also, if you look down here, number 4 is the difference rule, and we had both these rules for limits and derivatives. The third one here says that the integral of some constant times f of x is equal to that constant times the integral of just f of x. This says basically we can pull a constant outside of the integral sign. Okay, and the last one, number 5, which is where they made their mistake, really this should read, okay, this should read that the integral of a to b plus the integral from b to c, c should be on top here, equals the integral from a to c of f of x. Okay? So if you think about on the x-axis, if I go from 5 to 9, I'm just saying the integral from 5 to 7 plus the integral from 7 to 9 is the same as the integral from 5 to 9, as long as the function is the same. Okay? Sample problem. Let's suppose I have an integral. I give you what these areas are. I have the integral of f of x from 1 to -1. That's equal to 5. Integral from f of x from 4 to 1 equals -2. And the integral of natural log of x from 1 to -1 equals 7. First problem says I want to find the integral from 1 to 4. Notice that these limits are switched. So I can just take the negative of this, rewrite this as the negative of 4 to 1 of f of x, and I know what that integral is. It's -2, and the negative of that would give me a +2. Next one says I'm taking the integral from 1 to -1 of 2 f of x plus 3 natural log of x. Well, I should recognize this as the sum of two integrals, so I can split it up, and then I can also pull the 2 to the outside and pull the 3 to the outside. So what I have is 2 times the integral from 1 to -1 of f of x plus 3 times the integral from 1 to -1 of natural log of x. Those are 2 times 5 plus 3 times 7. Added up get 31. The last one is I'm taking the integral of f of x from 4 to negative 1. What I do is I split that up to from 1 to negative 1 of f of x and from 1 to 4. This is an application of that property that was wrong on the previous sheet. Okay, this I know is 5, and this I know as negative 2. Therefore, the integral would be 3. Get it? Practice problems. During class, let's work on page 373, numbers 23 to 34. Thank you, and see you in class.